Today I'm going to be covering all the stuff that you need to understand to get your head around carbon-13 NMR, that's nuclear magnetic resonance spectroscopy. I'll be finishing with a couple of practice exam questions where I'll give you tips on how to explain what you know on paper and get all the marks, so stay plugged in to the end. I'm also assuming that you've got a basic understanding of how NMR spectroscopy works. If not, you really need to go back and watch the first video in this series. I'm going to jump straight in by showing you the carbon-13 NMR spectrum for 3-methylpentane. The first thing we might notice is that all the peaks in a carbon-13 NMR spectrum are singlets. Now, we know that magnetically active nuclei, such as hydrogen and carbon-13, will split each other's signals if they're in close proximity to each other. This is known as spin-spin coupling. And this can make carbon-13 NMR spectra very messy and really tricky to analyse. As a result, carbon-13 NMR spectra are produced in such a way that any splitting is removed, and the spectrum is often described as being proton decoupled. As with proton NMR spectra, the chemical shift is measured against a reference signal from tetramethylsilane, and again I covered that in more detail in the first video in this series. We'll notice that the chemical shift, so we're talking about the x-axis here, for carbon-13 is much larger than that of proton, so the x-axis typically is running from 0 to 200 parts per million. With proton NMR, we're looking at an x-axis that runs roughly from 0 to 12 parts per million. The area under the peak is not necessarily proportional to the number of carbon atoms in a particular chemical environment. However, the height of the peak may be indicative of the number of hydrogen atoms bonded to the carbon. So we see that, generally speaking, not so much the case here, but carbon atoms with more hydrogens bonded directly to them have taller peaks than carbon atoms with one or no hydrogen atoms bonded to them. As I said, these are very general trends I'm going to be talking about over the next few minutes. So for each peak, we can determine the chemical shift by reading its value off the x-axis. And with reference to our data sheets, we can get some idea of the type of chemical environment that that particular carbon atom is experiencing. As with proton NMR spectroscopy, data sheets tend to come in two different varieties. The ones that look a bit like a diagram, so these are favoured by OCR exam boards, and the type that AQA prefer, for example, that are more like a table. I'm going to use this diagrammatic data sheet to outline a few trends. Carbon-13 atoms that are bonded directly to electron withdrawing groups, such as oxygen, nitrogen, chlorine, and bromine, tend to give peaks with a higher chemical shift than carbon atoms that are simply bonded to other carbon atoms. So an example of this type of chemical environment might be where I've got a carbon atom that is part of a chain, whether that be CH, CH2 or a CH3. Remember, it's the carbon atom's chemical environment that we're interested in. We also find that carbon atoms that are part of a methyl group have a lower chemical shift than those within methylene or methine groups. Now, with this data sheet, everything is lumped together. However, there is a slight trend, and it's worth bearing in mind that the carbon in a methyl group might have a chemical shift of around 5 to 20 parts per million. In a methylene group, so that's CH2, around about 20 to 30. And a CH, that carbon there, we'd expect the chemical shift to be around 30 to 50. However, here they're all kind of lumped together in one spread that runs roughly from 0 to 50 parts per million. The reason for the lower chemical shift? Well, we find that carbons that are part of a methyl group are more shielded from the external magnetic field, and hence they have this lower value. We also note that carbons that are sp and sp2 hybridized have a higher chemical shift than those that are sp3 carbon atoms. If that meant absolutely nothing to you, I do have a video on hybridization and valence theory somewhere on this channel. But all we need to realize for today is that carbon atoms are part of a double bond. So we've got some delocalized pi electrons, pi bonds being formed, as well as the sigma bonds. So we've got the C double bond O there, which is typical of aldehydes and ketones. Give a very high chemical shift, and often that's stand out on our spectrum. We've got the carbon atoms that are part of a ring system, again pi bonds, delocalized electrons, and the alkene functional group. So all of these carbon atoms giving us a much higher chemical shift. Now there is one important difference between these two data sheets that I need to point out. On the AQA table style data sheet, we have got a separate value for a carbon atom that's adjacent to the carbonyl group. On the OCR style data sheet, then it's just lumped in to this big range here. So this range here just for carbon to carbon goes from 0 to 50. With the AQA data sheet, this type of carbon, just the methylene type carbon, is in the 5 to 40 range in terms of parts per million. But if it was adjacent to a carbonyl group, then it gets its own specific range. Now that becomes important when we're describing the chemical environments of different carbon atoms in our molecules. So just be aware of that. The key is to familiarize yourself with the data sheet that you are going to be using in your exam. As always, I'm a big believer that the best way to get your head around all of this is just to jump in and match up some molecules to some spectra as best we can and practice using our data sheets. So we're going back to our spectrum for 3-methyl pentane. As I said earlier, there are 4 peaks on the spectrum. So that is telling me I've got 4 different chemical environments in my molecule. This is a common type of molecule for an exam question because it is symmetrical, which means that this carbon and this carbon, so carbons 1 and 5 in my chain, are equivalent. They're in the same chemical environment, so they both contribute to the same peak. Similarly, carbon atoms 2 and 4 in my chain are equivalent. They contribute to this single peak. And then I've got 2 carbon atoms that have got their own unique chemical environment. The CH in the middle of the chain and the methyl group that makes up the chain. If I were describing this spectrum in the exam, I would read off the chemical shift for each of these as accurately as I can off the axis. So, for example, I might say that the carbon atoms in the methyl groups at either end of the chain are equivalent and give a single peak at, well, what have we got there? I'm going to say that that's round about 11, okay? This peak, so we've got a peak at chemical shift 11, and that is for a carbon or a carbon atom, and it's got its unique chemical environment. And reading off either data sheet, it doesn't matter which, it's for just a basic carbon that's part of an alkyl chain. Now, on the data sheets, as we've seen before, the carbon atoms that are responsible for the peak, whichever data sheet we're looking at, are given in bold. But it's really hard to write in bold in an exam, so underlining is the next best thing. So in reality, I probably wouldn't draw it out like so. I would for a carbon, and I would underline just to show that it's a carbon is part of an alkyl chain. Now, on the data sheet, the chemical shift range for all of these carbons, because they are all in an alkyl chain, is simply 0 to 50 parts per million, 5 to 40 parts per million, depending on which sheet you're reading. So if I were making predictions, that is all I'd be able to say, that there are 4 peaks and that they are all going to be within the range of chemical shift, say 0 to 50 parts per million. It's only because we have more information that we're able to actually assign a particular peak to a particular carbon atom in this example. Moving on to look at the spectrum for methoxyethane. Now, the first thing I can see straight away is that there are 3 unique carbon environments. So that's what I would write in my answer describing this. So 3 unique carbon environments because there are 3 peaks on the spectrum. Now that might seem obvious, but you get marks for writing it, so write it down. Now clearly this carbon on the end of the chain is going to have the lowest chemical shift. It's just part of a carbon-carbon chain, and we see that here with its chemical shift of, well, whatever that is. Yeah, I'm getting around about 11 parts per million again. A common mistake is to look at carbon atoms such as the CH3 and the CH2 and go, they're also just part of an alkyl chain. Look, the CH2 is part of an ethyl group. This carbon atom is part of a methyl group. And to predict, for example, that their peaks would also be in the same range, so that's around about 0 to 50 parts per million, as we see for a carbon, for our lowest type of carbon in terms of chemical shift. However, the important thing here is that these carbon atoms are directly bonded to oxygen. So if we go back to our data sheet, we are looking at the chemical shift being somewhere in the range of 50 to 90 parts per million. And that is indeed what we see for both of them. So look at your molecule carefully, read the data sheet even more carefully. Now, if there's one thing that you'll notice when you start going through lots of past papers, is that examiners love a benzene ring when we're doing carbon NMR spectroscopy. A substituted benzene ring, even better. So this is chlorobenzene, is my little chlorine atom. Because I've got a substitution, in this case chlorine for hydrogen, the carbon atoms in this ring are not all equivalent. We've got 4 different carbon-13 environments here, and we've got 4 peaks. They're all very close together because they're all in the range of 110 to 160 parts per million, ppm, if you have a look on your data sheet. But they're giving us individual peaks because their chemical environments are unique. We've got these 2 carbon atoms, so if we make this carbon 1, we'll go around clockwise, 1, 2, 3, 4, 5, 6. Then carbon atoms 2 and 6 are equivalent. So that gives us 1 peak. They're both contributing to 1 peak because they're in the same unique chemical environment. And then we can see that carbon atoms 3 and 5 are equivalent. They are both giving us one peak. And finally, carbon atom 4 is unique and carbon atom 1 is unique. So 4 different chemical environments for our carbon atoms, 4 peaks. Pointing out that pairs of carbon atoms are equivalent is worth marks, so tell the examiner. 1-phenyl propan monoene. It looks like a scary molecule. The carbon NMR spectrum looks intimidating, but we can break this down quite easily. We have all the tools that we need now. The first thing to say, always before you jump in and start giving peaks chemical shifts and telling me what type of carbon environment we've got, is to state that we have got 6 peaks on the spectrum. That means 6 unique carbon environments in my molecule. These are good phrases to commit to memory. The standout is always going to be the carbon that's part of the carbonyl group, because if we look on our data sheet, that always gives us a very high chemical shift. So that's a straightforward one to assign a particular peak to. Then we have got our CH2 and our CH3. Now, if you are looking at the OCR data diagram, shall we call it, then if you remember, both of those carbons are in environments that are simply described as being carbon-carbon. And we get a range of around about 0 to 50 parts per million. Well, they both fall nicely into that range. However, if we are looking at the AQA data table, then this carbon atom is adjacent to a carbonyl group. So we'd write it as the carbonyl group and then the carbon, and underline it's the carbon adjacent, not the carbon in the carbonyl group. And this is given a chemical shift range of 20 to 50 parts per million. And once again, it falls neatly into that range. So read your data sheets carefully, write it down carefully. And then we move on to our benzene ring. Well, if we look at our benzene ring, then once again, just with like with chlorobenzene, because it's substituted, my carbon atoms are not all equivalent. If I were doing this in the exam, I would probably do a quick sketch of it and number my carbon atoms, and then I can see, I'll say quite quickly that carbon atoms 2 and 6 are equivalent, and carbon atoms 3 and 5 are equivalent. Carbon atom 1 is unique, carbon atom 4 is unique. In this particular spectrum, it seems that the peaks for 2 and 6 and the peak for 3 and 5 is the same. They're giving us the same chemical shift, and then the individual carbon atoms are giving us their own peak. A good exam-style answer that describes carbon-13 NMR spectrum must cover 2 things. Firstly, that you've linked the number of peaks on the spectrum to the number of unique carbon environments. It seems obvious, but so many students fail to bother to mention it. And secondly, you've used a datasheet to identify the type of carbon for each and every peak. You've given us the chemical shift, if it's read off the spectrum, or if we're making predictions, then we would state a range in which we'd expect the peak to be seen. Moving on to the first of my exam questions. 4-hydroxycyclopentwanene, that is a mouthful, and cyclopentanone are isomers with a molecular formula C5H8O. Explain, with reference to the datasheet, how carbon-13 NMR spectroscopy could be used to distinguish between the two. So we already know the 2 things that we're going to have to put into our answer. How many peaks we'd expect on each spectrum, and we need to predict the chemical shift range for each type of carbon atom. So in my mind, the first job is to number our carbon atoms so that when we start to put our answer together, it's immediately clear both to us and the examiner which carbon atoms we're talking about. So let's start with our 4-hydroxycyclopent-1-ene. The name pent-1-ene tells me that that's the main functional group. It's an alkene with a hydroxyl side group. We number alkenes so that they have the lowest pair of numbers in terms of where they are in the carbon chain, which makes this one number 1, 2. You could go clockwise or anti-clockwise in this example. 3, 4, hence the 4-hydroxy, 5. And for my cyclopentanone, well, the main functional group is carbon number 1, 2, 3, 4, 5. Again, it wouldn't matter whether you went clockwise or anti-clockwise. So how many different carbon environments have I got in each of my molecules? Well, I can see that my molecules are symmetrical, but we do have the substitution if we kind of think in terms of the substituted benzenes that we've been looking at. So I could see that in our first molecule, carbons 1 and 2 are equivalent. Carbons 3 and 5 are equivalent because they're either side of the hydroxyl group. And carbon number 4 there is unique. So I'm looking at 3 peaks because we've got 3 unique carbon environments. How about our cyclopentanone? Well, clearly the carbon here at the top is a unique. And then once again, as my molecule is symmetrical, I can see that carbon atoms 2 and 5 are equivalent. They share a chemical environment. And carbon atoms 3 and 4 are equivalent because of their position in this ring system. So once again, 1, 2, 3, I would expect 3 peaks because I've got 3 unique carbon environments. And our answer continues in exactly the same way in describing the range of chemical shifts that I would expect the peaks of cyclopentanone to turn up in. So we can start by saying carbon, I'm going to abbreviate this somewhat, carbon atoms 3 and 4 are equivalent. And they're going to give us 1 peak. And the chemical shift range is going to be 0 to 50 parts per million. And this is for a basic carbon that's got a single bond to another carbon. That range here that I've given you, 0 to 50, is off the OCR datasheet. If it were the AQA datasheet I'd be using, it's going to be 5 to 40 parts per million. Then we can also say that carbon atoms 5 and 2 are equivalent. Once again, we're going to get 1 peak. This is where we need to be a little bit careful. If I'm using the OCR datasheet, then once again, they're just simply a carbon single bond carbon type of carbon. But if I'm using the AQA datasheet, then our peak is at somewhere around, what was that range, 20 to 50 parts per million, because they are a carbon that's adjacent to a carbonyl group. And on that datasheet, it gives us a slightly different range there, and it stands out. And then the final point I would make, I'm going to put it up here because I've run out of space, is that carbon atom number 1, is in a unique chemical environment, and it's going to give us a peak at around about the chemical shift 190 to 220 parts per million. and that's for a carbon atom that's directly double bonded to an oxygen. Okay, in this case it's a ketone, it's part of a carbonyl group. And that would be the standout difference between the spectrum for this molecule compared with this molecule over here. And on to our last exam question walkthrough. We've got pentane reacting with bromine. It's giving us a mixture of 3 straight chain isomers with the molecular formula C5H11Br. So we've got a direct substitution of a bromine atom for a hydrogen atom. Deduce the structure of the isomer that's responsible for the spectrum below. Explain your reasoning with reference to the data sheet. So by now we should realise that that means it wants some chemical shift values linked to our unique carbon environments. So the first thing I can see on my spectrum is that I've got 3 peaks. So I'm looking for an isomer that's got 3 unique carbon environments. The first step is to draw out our 3 isomers. The molecule responsible for this spectrum is either 1 bromopentane, 2 bromopentane, or maybe 3 bromopentane. My first job is to figure out how many different or how many unique carbon environments each molecule has got, because the one with 3 is the one responsible for this spectrum. If we take 1 bromopentane first, I've got 1, 2, 3, 4, 5 different carbon environments. Now, they are all, no, they're not all. The peaks for these 4 carbon environments are all going to be in the range of 0 to 50 parts per million. And the peaks are likely to be all very close together, but they are 4 different or 4 unique chemical environments, because we've got a carbon that's adjacent to a carbon bonded to a bromine. I've got a carbon that's part of a methyl group that's on the end of my chain. That's likely to give me the lowest chemical shift peak. And then I've got 2 CH2s. These 2 carbon atoms are not in exactly the same chemical environment. Carbon atom number 3, it's sandwiched between 2 CH2 groups, and carbon atom number 4, it's sandwiched between a methylene and a methyl group. If I have a look at 2 bromopentane, I've got exactly the same thing happening. 1, 2, 3, 4, 5 unique carbon environments. Although I've got 2 methyl groups, these carbon atoms are not equivalent, because this carbon atom is adjacent to a carbon atom bonded to a bromine. So once again, the peaks for carbons 1, 3, 4 and 5, although they are all of the carbon single bond carbon type of environment, and they're all going to be giving me a peak somewhere in the range 0 to 50 parts per million, they are not equivalent. So that means that I'm expecting 3 bromopentane to be my winning molecule. So I've got rid of the first 2 isomers. We've already agreed that they are not the ones we're looking for. Let's have a look at 3 bromopentane. Well, clearly I've got 1 unique carbon environment for the carbon that's bonded to the bromine. And if I were to look on the data sheet, I would expect that to give me a peak somewhere in the chemical shift range 10 to 70 parts per million. So that would be carbon, bromine, and my chemical shift 10 to 70 parts per million. And indeed, we see that particular peak just there. If I were to take my other carbon atoms, I'm just going to go back and change that actually. We're going to call that carbon 3 since it is the 3rd carbon in the chain. This is going to make a little bit more sense, I think. So if I take carbons 1 and 5, we can see that they're equivalent because I've got a symmetrical molecule, which means that carbons 2 and 4 are also equivalent. So I can say for this molecule, I have got 3 unique carbon environments. We can say that we have got, we've already identified the chemical shift for the carbon bonded directly to the bromine. We could say that carbons 1 and 5, so carbon atoms 1 and 5 are equivalent, giving us 1 peak. Chemical shift range around about 0 to 50 parts per million, and that's for a carbon in an environment where it's bonded, single bonded to another carbon. And then I'd be saying the same thing for carbon atoms 2 and 4, that they're equivalent, that be giving us 1 peak, chemical shift in the same range. They're still carbon atoms singly bonded to other carbon atoms, but they're adjacent to the bromine, so that means that their chemical shift is likely to be a smidge higher than that for the peak for carbon atoms 1 and 5, because they're very slightly closer to that electron withdrawing group. So we can say with some certainty that this is the peak for the carbon even bonded to the bromine. It would seem that this is the peak for the carbon atoms at either end of the chain that are part of the methyl group, and that would leave the peak in the middle, slightly raised as we have explained, responsible for, or the result of, the carbon atoms that are part of the 2 CH2 groups. So just to recap, in order to get full marks, I have identified that we've got 3 unique carbon environments because I have 3 peaks on my spectrum. Write it out. I have shown that carbon atoms 1 and 5 are equivalent. I've identified the correct type of carbon environment from my data sheet and given the correct chemical shift range. And we can say that that peak is round about the actual peak. So it's giving us a peak at chemical shift, should we go with 12 parts per million. I've done exactly the same for the carbon environment for the 2 CH2 groups, and finally for the carbon directly bonded to bromine. And I finished by saying this NMR spectrum belongs to 3-bromopentane. It'd be silly to get all the way to the end of the answer and not actually make it really clear which one I'm assigning to my spectrum. If you follow the link in the blurb below to the Crunch Chemistry website, you'll find a set of notes for this video with these perfect template answers written out in full, which might be of use to you, as well as some practice questions and all sorts of other useful bits and pieces. If this has been helpful, then please hit the like button and subscribe. It makes a big difference to a small channel like us. And spread the word. That would be amazing. I look forward to seeing you next time.